Again, welcome to Math 415 differential equations and special functions. So I'm going to show you what we have going on for in the course, what resources are available, and then I'll get into the actual material. So I'm going to share hopefully the whole screen, or actually this browser will be enough. Okay, so here's we have the site on Canvas, but there's actually two course websites. Kind of used to maintain before doing things in Canvas all the time, and I figured I would keep that going. So here, so this link here from the Canvas homepage, the course website, that's my external site, and that's what we have here. And the all have the same information, so it's up to you as to which one you want to use. So here I have certain things might be easier to obtain here. Like here's a whole lecture schedule. On this page, I will post my notes and links to the recording. And I'll do the same in Canvas. All the information about the assignments is here. I'm going to roll about in Canvas one assignment at a time. Like this first one is already there. It's not due for a while. And then I may revise the list of problems assigned later on. So don't jump ahead. And then, okay, don't admit again, I might have materials there later. If there's any mistakes that are found in my notes, like I'll post them there. Here's the information that you have in syllabus. Okay, but all this, of course, is in Canvas too. Oh, yeah, I have a PDF. Whoops, I didn't want to actually click on that. PDF for textbook. So don't have to buy it. And then I'll have links on this page to information about each class meeting. So the before class will just be a link to the Cisco WebEx meeting. After class, or like later in the evening, I'll post the notes and videos here too. Okay, and you can see the assignments there. So only this first one is published. The later's other ones will be coming later. I'll also post links to the homeworks right here on this page, just so things are conveniently accessible from this page. As for the course information, I'll get to the content in just a little bit, but as far as the administrivia, okay, I mean, we have these prerequisites, as I mentioned, this is a second ODE course, so the follow-up to Math 285, and I know not everyone has these already in the background, but don't worry about that. I tend to assume that students don't remember anything from prerequisites anyway, and so just go ahead and cover what's needed, because in practice that's worked so much more easily. Okay, textbook. Okay, there are no tests in this class. It's just written homework assignments. Yes, I figured you'd like that, Chandler. Everybody else here does too. So the kind of problems that you'll see in a homework are not the kind that really let themselves to an in-class test, like during a short time frame. So I thought, well, if I'm going to give a test, I feel like I want to make it a take home, but then it's just a homework assignment again. So there we go. Okay, and then all of the other info that's supposed to go in the syllabus. I mentioned my syllabus document that's on Canvas. I don't think I do have it mentioned here. Lowest homework grade will be dropped. So there will be 12 assignments altogether, so the top 11 will count to the grade. Now, those of you who've had me in a class before know that while I do put out due dates, they're of the advisory form. So, because even though things are very different than they were in 2020, but we still are in a pandemic. There's still a lot of things that we have to deal with. We're all under a lot of duress, and I feel like that aspect of it, both COVID and a lot of things about it have changed a lot during these few years. That everything that's going on, does take a significant toll on our mental health, and I try to take it into account. So I do encourage you to try to get these in by these. These due dates are meant to help you pace yourself so that you don't fall too far behind, because then you're just going to go through a lot of things at the end of the semester when you have finals coming up. But if you have a lot going on in your other classes and you want to take some more time to get these things in, then you can go ahead and do that. So I'm flexible, but if you try to take too much advantage of that, besides the inconvenience that it causes me, it will be detrimental to you as well. So I urge you to do some judgment about that. Okay. So the class setup is quite straightforward. That said, are there any questions about how the class will be run? Now, since we have, last time I checked, 2 students enrolled at Golf Park, so on occasion, like maybe once a month or so, I'll be making an appearance down there, and I will teach from there. So choose some given book. Okay. I'll try to do my best to check the chat now and then, but when I get really into the notes, it's possible that I might miss something. So feel free to, if you're attending online, feel free to just yell out if you need my attention. Okay. Now I'll put up the notes. Okay, so the way it's going to work with the notes, so this is what I'll actually be covering. That's gleaned from the text and other things. And those of you who have been in class before are familiar with this process, where we'll modify these as I go, as needed, based on any questions that are asked during class, or if I spot a mistake, something like that. So these notes are like a living document, if you will. So this editor lets me enter like the mathematical content and have it rendered immediately, which is one thing I like about it. About those of you who have been in class before know that this program can also cause me some frustration. So I apologize for any outbursts that went into because of that. But overall, this has been very, very helpful. It's idiosyncrasy aside. So the final version of these notes, that whatever form it's in by the end of class, that's what will be posted on in Canvas on the other site. So if you miss a class, you're very well covered. Okay. Now, I was kind of surprised. I last taught this class back in 2013. This class has not been offered very much since then. It used to be a requirement for physics students. I don't know if we have any of those here this time, but I think they dropped it as a requirement. And the powers that be just wanted to offer something different in the schedule, and therefore here we are. So I have in these notes 7 pages, this is for today, 7 pages worth of content, which is generally more than I can possibly cover in a day, even when I do start on time. So I'm not sure how it's going to go. I don't really want to rush through this, and I know it's not going to be the case every day. When I looked ahead at other notes that I have down the road, it's not so much. But so I'll do my best to go at a reasonable pace and see where we end up. There's going to be some introductory looking out for concepts that we'll be needing in the near term. So if I were to try to describe this class in a nutshell, it's about series solutions of ordered differential equations, or ODEs. It's very different than what you're accustomed to from your first differential equations class, because in our case, Math 285. So in that kind of class, you would learn about first order ODEs, then second order, and what you would find is that the general solution of those kind of ODEs would be a linear combination of n functions where n is the order of the ODE. So for instance, in the second order ODE, you would have two linearly independent solutions. I'll talk about linear independence a little bit later. And you would find some combinations of those that would satisfy the initial conditions. And those functions would be like exponentials, or possibly sines and cosines, or combinations of the two. By contrast, if we represent a solution of an ODE as a power series, and you may recall seeing power series in Calculus 3, there's some advantages to that because we're working with simpler functions, polynomials, which is nice for numerical evaluation and other kinds of manipulations, as opposed to exponential or trigonometric functions. So because polynomials are so much easier to work with, like term-by-term integration or differentiation or evaluation, whether it's done by hand or on a computer. The differential equations that you saw in the introductory course generally had constant coefficients. Certainly higher order equations did. By working with series, it makes a solution of some variable coefficient problems possible. And we'll come across certain ones that are important in applications. We could get a simple approximation of a solution. If we have an infinite series, a power series that represents the exact solution of the differential equation, we can cut it off at a certain point, and then we have a useful approximation. And that can help us understand how solutions behave. So these are some advantages to this perspective compared to the Math 285 approach. Now, we're going to learn about certain special functions, because this class is called Differential Equations and Special Functions. The special functions in question are actually solutions to certain ODEs of interest in mathematical physics. As I mentioned, this class was a requirement for physics students at one time. So one kind of function we'll learn about is a Bessel function. Another are certain kinds of polynomials. One popular example of this is the Legendre polynomials, and there'll be a certain number of families of polynomials we'll learn about too. They're actually called orthogonal polynomials. Now, orthogonality is something that at this point in the math curriculum, the only place you likely would have seen orthogonality is in Calculus 3. And in that case, orthogonality has a concept of very limited scope. And we're going to generalize that to a large degree, actually today, right now. Okay, so what is orthogonality as you know it up to this point? Just from a typical calculus sequence. There's really not much to it. You may recall taking the dot product of two vectors, and that's where you multiply corresponding components of a vector and add them all up. And if the dot product of two vectors turned out to be 0, then geometrically, the two vectors are perpendicular in n-dimensional space. But the term that's used to describe them is orthogonal. If you have two vectors that are pointing in different directions, then those vectors we can call them linearly independent if they're not parallel. Orthogonality you can think of as extreme independence. There's independence from one another as they can possibly be when they're orthogonal. So in other words, not just pointing in different directions, but informally, and this is a very non-rigorous description here, they're pointing in completely different directions. Now, I'm also going to use the term vector space a lot more broadly than you're accustomed to. You would have seen vectors in calculus, like calculus 3, calculus 4. Vectors in 2 or 3-dimensional space is what you deal with in those classes, and pretty much only those kind of vectors. But the vector there are a lot of things that can be a vector. There are a lot of different collections of entities that can be described as a vector space, and that they behave as conventional vectors do. And that's something we're going to get into early on in this class. A vector space in which the vectors in question are functions rather than points in 2 or 3-dimensional space. So we're going to learn about function spaces. So that's the very first thing that I'll really get into. Vector spaces in which vectors are functions, so we refer to them as function spaces. And for that, I'm going to describe an abstract vector space. Okay, what does it take for a collection of objects of any kind to be a vector space? What you really need are to be able to perform 2 operations on them. You need to be able to add them. So if you can define the concept of addition for whatever objects you're dealing with, then you have an addition operation. And then also scaling of what you want to be a vector. So you're taking a vector and multiplying it by a number. Now, I'm going to call that number a scalar. It's literally just a number. But I refer to it as a scalar because of what it's being used for. It's being used to scale a vector, to change its magnitude or possibly its direction too. For instance, if you multiply a vector by a scalar as a negative number, then your vector is pointing in the opposite direction. Okay, so if you can make these 2 operations make sense in a way that follows the various laws of addition and multiplication, then you're good to go. You have a vector space. And what exactly does that mean? So addition must be commutative, must be associative. There has to be an identity element, some vector you can add to any other vector that doesn't change it. So that would be the 0 vector. So in 2 or 3-dimensional space, that would be the point 0, 0, or 0, 0, 0. So as long as your collection of vectors has some additive identity element, then that condition is satisfied. You have to have a notion of an inverse, an additive inverse. So for a given vector v, as long as you can define what it means to be minus v, then that property of the vector space is satisfied. And all that means is you take your vector v, you add its inverse minus v to it, and you get the 0 vector, the aforementioned additive identity element. I will give examples of this. Right. But you're also welcome to chime in with questions at any time. The scalar operation has to follow the usual rules of the road for multiplications. So that's the distributive law. There must be an identity element for scalars, which would be the number 1. So you scale a vector by 1, it doesn't change it at all. So that's the first thing. Is you need these 2 operations. You need sensible definitions of them that behave as you would expect. Now, this next property is a big one, very important. For it to be a vector space, the operations have to be what's called closed. We must have a property of closure. All that means is, if you take two vectors and add them together, the two vectors from your set add them together, or if you take a vector from your set and you scale it by some number, that must keep you in the set. So, that's a set of property of a vector space. I'll give you an example of something that is a set of vectors that is not closed. So we're talking about vectors being kind of vectors you're familiar with. Points in R3, for example. Suppose I choose not all points in R3, not all three-dimensional vectors, but just certain ones. And let's suppose I require that the last component of the vector is equal to 1. But sudden partial darkness there. So, if I take two vectors whose last element is 1 and add them together, the last element is 2. So we don't have closure in that case because that addition of those two vectors that are in the set give me a vector that is not in the set. So a set of all vectors with last component equal to 1 is an example of a set that is not closed. Okay. I'll go ahead and write that in here. An example like that further down. No. Okay. That is not closed. So that poses a question to you all. What if I choose all points in R3? And so in R3, that's referring to the z component. What if I say take all points in R3 where the z coordinate of the last element of the vector is equal to 0? Is that closed under addition? Like if I take two such points that satisfy this condition and add them together, is addition closed in that case?
Yes, sir.
Yes, because you take 2 points, two vectors whose third component is 0, you add them together, it's still 0, still in the set. If I scale it by any number, I'm going to scale that last component by whatever number it is. I'm still going to end up with 0, still in the set. So this leads me to one quick way to, it doesn't prove that a set is closed, but it's a way to rule out a set that's not closed. Must contain 0 vector. You have a set of objects that you want to call a vector space. If it doesn't include any notion of a 0 vector, it can never be closed. It's not possible. All right. So if you have a set of objects where you have these two operations, addition, scale, multiplication, and it is closed, then that makes a vector space. So a vector space that you're familiar with from prior classes is this one, Rn, generally n being 2 or 3. And here are the operations that you have. So if U is a vector from Rn, and so is V. Here are their components, and coordinates for each one. Adding is just adding corresponding components together, and that's how we define some U plus V. Scalar multiplication, we take a vector in Rn, multiply each component by a scalar, which is alpha. Alpha is just a real number. Let's see if I can note that here. And you can show that these operations are closed, that you take any two vectors in Rn, you get a vector in Rn, you scaling vector in Rn, the result is also in Rn, that's a vector space. In this case, all the coordinates or components are real numbers, but I can make them complex numbers. That's another vector space, a different vector space, that means Cn. Once in a while, rarely we'll be dealing with complex numbers in this class. Any questions up to this point? Now I have some more examples of vector spaces, but these are kind of vector spaces you have not seen yet, because the vectors involved are functions. So if I could describe a set of all polynomials of degree at most n, so I choose n arbitrarily. So like suppose I want a set of all quadratics, so that would include all polynomials of degree at most 2. So all quadratic functions, linear functions, constant functions, and 0. So set of all polynomials up to a certain degree, that is a vector space, because we can certainly define what it means to perform addition, scaling, multiplication. We know how to add functions. We know how to scale functions. Those are things that we know how to do already. We're just calling that a vector space. Now, keep in mind, I've stated degree at most n. Like, suppose I focused on polynomials of a particular degree, like all polynomials of degree 2. Just that set of polynomials, that's not a vector space. It's not closed. Because I can take one polynomial from that set, x squared. Another polynomial also from that set, minus x squared. Add them together, I get 0. Or I can take two sets of polynomials, quadratics, I can make 2 and add them together, and the quadratic terms cancel. And now the sum is of lower degree. So if I say I look at some polynomials of degree at most n, then I'm covered. But if I say exactly n, I'm not. That's not a vector space. And here's just a quick explanation as to why that is closed. Because if you form addition or scale multiplication on polynomials, you'll never increase the degree. Like I said, it might decrease it, but never increase. It'll always be and adding polynomials always gives you a polynomial, as opposed to other operations that do not, like division. But we don't care about that. We only care about addition and subtraction and scalar multiplication. So you don't deal with multiplying vectors together. That's not an operation we consider. Okay, that's one example of a function space. Here's another. All power series that are convergent on a certain interval, in this case the interval -1 to 1. That is a vector space, because if you take a convergent power series that's convergent on a certain interval, then you take 2 of those and you add them together, the sum will be convergent. Whereas if you take a convergent power series and scale it, that's still going to be convergent on that same interval. So closure is satisfied. And certainly we know what it means to perform addition, scale, multiplication on power series. What you're doing is you're adding the coefficients or scaling the coefficients. In this case, it's natural what the operations would be. I guess linear algebra class sometimes the textbook might have problems where, like, oh, here's some funky addition, scale, multiplication operations, and does this define a vector space? You got to show, is it closed or is it satisfied? various properties. We're not going to bother about here. I have enough weird stuff to provide you. Yet another example. Suppose you consider all continuous functions on a certain interval. This is a notation used for it. This is something that pops up a lot, so to get used to it. Capital C followed by a domain like the interval AB that is commonly known to be the set of all continuous functions, set of all functions that are continuous on that interval. Because if you take two continuous functions and add them, the sum is continuous. If you scale a continuous function, the scale function is continuous. So it stays in the set. All right, so you know what I've got. All right. Now, so here's some essential linear algebra concepts that we'll need. Okay. Because it's helpful to be able to describe a vector space in terms of certain key vectors that can be used to describe all the rest. And you may have already seen this in other classes or physics. Suppose you have a three-dimensional space. If you have the vectors that are commonly referred to as I, J, K, I is the vector 1, 0, 0, that pointing in the x direction. And then J is the vector for y direction, 0, 1, 0. And then K is the vector for z direction, 0, 0, 1. You can use those three vectors to describe all vectors in three-dimensional space. So we like to be able to do that in general, like have a set of certain vectors that describe all vectors in the space. So if I have a set of vectors like v1, v2, and so on, then what I can do is take those vectors, multiply them by scalars, c1, c2, etc., and get a new vector. This is called a linear combination. So if you anytime you have a set of vectors, you scale each of them and add them up. That's a linear combination. The numbers that you're scaling by, those are called coefficients of the linear combination. So this is a hugely important concept. We're going to see linear combinations all the time. So what we'd like to be able to do is express any vector in your vector space as a linear combination of select vectors of importance, like this I, J, K. And better yet, if that linear combination could be unique, that's even better, because that gives away those coefficients, a unique set of coefficients that describe your arbitrary vector. That is an alternative description of the vector itself. And that leads to the concept of linear independence. So what does linear independence mean? So here's a formal definition. It's not the most helpful necessarily, but I'll start with it and go from there. So suppose you have a set of vectors, v1, v2, up to vn. It's linearly independent if the only way to take a linear combination of them and obtain 0 as a result is if all the coefficients are 0. Now, if you were to set the coefficients to 0 and take this combination, then you wouldn't get 0. But the key is that it's the only way to get 0. And what that means is, it's not possible, if this is the only way to get 0, that means it's not possible to solve for any one of these vectors in terms of the others. Because they're independent. Like if I could express v1 in terms of v2 for vn, I don't need v1. I can toss it out. It becomes redundant. If a set of vectors is not linearly independent, we say it's linearly dependent. I need to scroll ahead for a bit. All right, I'm going to give us the simplest example of the set that is not linearly independent. Okay. So let's look at two vectors, v1 and v2. Where one of them is a scalar multiple of the other. So the v2 is equal to a constant times v1. Because then, in that case, what you have is cv1 minus v2 is equal to the zero vector. So here we were able to find non-zero coefficients of c in this case and minus 1 in this case, and took a linear combination like this one, wind up with a zero vector. So that is that means they're not linearly independent, they're linearly dependent. And I'm going to emphasize that here so there's no confusion. So if you have any two non-zero vectors, they are linearly independent if and only if they're not parallel. And type. But when you have a set of more than two vectors, then it gets a little more difficult to determine if we're linearly independent or not. Okay, so that's one key concept, linear independence. Here's another one. What it means for vectors to span a space. So if I have a set of vectors, v1, v2, vn, not commenting on whether they're linearly independent or not, some set of vectors, if you can use those vectors to describe every single vector in your space, V, capital V, by linear combination. So any vector in the space can be described as a linear combination of these. Then what that means is these vectors span the space. And in fact, we can define the span of a set of vectors to be a set of all possible linear combinations of them. If the span of a set of vectors is equal to the vector space, that set of vectors spans the space. So now, what I want to do is put two concepts together: linear independence and spanning. So if I have a set of vectors, v1, v2, which, and I don't cut it off because it could be a finite set or an infinite set. Doesn't matter. If the vectors are linearly independent, and if they span a vector space V, then they form a basis for V. So that's what it means to be a basis. A set of vectors is a basis if it spans a basis for a space. So the concept of a basis is tied to a vector space. You have to be a basis for something. It can't be a basis by itself. Set of vectors is a basis for a space if it spans a space and is linearly independent. And I want to take a moment to explain the role of both criteria in terms of linear combination. Because the set spans V, any vector in V is a linear combination. Okay, so because this type spans V, any vector V is a linear combination. Okay, so that's why spanning is important. Because this set is linearly independent, what that means is that linear combination is unique. Right, so spanning covers existence, linear independence covers uniqueness of a way to describe an arbitrary vector space in terms of your set, your basis. This leads to the notion of dimension of a vector space. Generally, a vector space can have infinitely many possible bases. But they must have one thing in common. They must all have, must all have the same number of elements. So a number of elements is called the dimension. So for example, in this vector space R3, I mentioned one basis, ijk, but you can come up with all kinds of other bases for R3. They'll all have 3 elements. So in fact, any set of 3 linearly independent vectors that you can come up with in R3 is a basis for R3. Now, if you have now the number of elements in your basis is finite, but it's a finite dimensional space. Otherwise, it could be infinite dimensional. So, for example, set of all polynomials up to degree n. Any basis for that space has dimension n plus 1. So, for example, polynomials up to degree 4. Right? Here's your basis: 1, x, x squared, x cubed, x to the 4th. 5 elements. So that makes a basis. But if you're talking about all polynomials, regardless of degree, any degree at all, that is an infinite dimensional space. And you can still describe it using the basis of your monomials: 1, x, x squared, x to whatever power off to infinity. So all non-negative, x to all non-negative integers. Then, so that's an interdimensional space, and then that is one basis for it. So questions about linearly independent, span, basis, dimension, in your algebra things? It gives you a preview. And then so here's an example of talking about P3. So this is a set that spans P3 because you can describe any polynomial of degree 3 or less using a linear combination of these. These would be the coefficients. But is this set linearly independent? Well, let's take a look at that. So let's suppose I take a linear combination of these polynomials, these monomials, and set it equal to 0. Well, in order for this to be 0, right? And it has to be 0 for all x. And I'm not computing roots here. I want this to be the 0 function. Function equals 0 for all x. Well, if I set x equals 0, and these 3 terms drop out, and then the c0 equals 0. So this coefficient has to be 0. Then what I can do is I can substitute 3 other values of x in here, and I get a system of 3 linear equations in the three unknowns, C1, C2, C3. And on the right-hand side, and that equals 0 in all three cases. So what you can show, this is what comes from linear algebra, is that, oh, a typo here, you can actually show, by substituting three of our x values in this equation, that C1, C2, and C3 must also all be 0. Basically, you get these three equations for these coefficients, and you do elimination and substitution, and that's the only answer you can get that works. So, so this set, 1x, x squared, x cubed, is linearly independent, because the only way to take a linear combination of them and get the 0 function is for all these coefficients, C0, C1, C2, C3 to be equal to 0. Therefore, because this set spans P3 and is linearly independent, it is a basis. But that's not the only basis. Here's another. These four polynomials, 1x, the first two I was saying, but then I have 2x squared minus 1, 4x cubed minus 3x. These are called the Chebyshev polynomials. They are linearly independent also. These are polynomials that have very interesting properties. I don't recall if I really get into them more in this class, but in other classes I certainly do. Very wonderful. But this is another example of, there's all kinds, I could come with any four polynomials of degree 3 or less that are linearly independent. They must all have different degree. That's one criteria. As long as they're linearly independent, they form a basis, because any basis for this function space of polynomials of degree 3 has to have 4 elements. Questions on that? The space I mentioned earlier, all power series converge from -1 to 1. That has this set of infinitely many monomials as basis. So 1x squared all the way to x to any power. That's a non-negative integer. So it's possible to show, it requires proof by induction from what we do here, that this set not only spans all power series, but is linearly independent. And what that means is any power series is described uniquely in terms of its coefficients, which you probably would guess that anyway, but this proves that that's true, that you can identify any power series through its coefficients. That the coefficients are enough to describe it uniquely. How much am I not going to get to today? Oh boy. I'll figure out how to deal with that later. Okay. As I mentioned before, with dot products, this operation you will learn about in calculus 3 probably. I'll teach you there. For the dot product of two vectors in n-dimensional space, so ordinary vectors, well, you dot v, you just multiply corresponding components and you add them all up. That's one formula. Another formula for them is the magnitude of u times the magnitude of v times the cosine of the angle between them. I remember, like, this is a formula that I learned in math class. This is a formula that I teach in a physics class. Go figure. And here's some properties that the dot product has, at least on Rn. So it's very important that we're assuming in real vectors, not complex. That if you take a dot product of a vector with itself, that'd be u1 squared plus u2 squared, and so on. That is the square of the magnitude. It's sum of squares here. We have a distributive property. It's commutative. u dot v is equal to v dot u. And if you scale a vector by a constant c, then that scales the dot product by c. So you can pull constants out of dot products. If you would be a perpendicular, the angle between them has a cosine of 0. So the dot product is 0, and we say that they are orthogonal. So that's, like I said, it's going to be very important to us in a broader sense. So what I want to do is take this notion of a dot product, which provides a notion of orthogonality, in other words, total independence, and be able to generalize that to a function space. Because this dot product operation that tells me if two vectors in Rn are orthogonal is defined in terms of a component of u and v. I don't have any obvious way to use this operation when the vectors in question are functions. So I need to define a whole new operation. But I can do that. And here it is. It's called the scalar product, also known as the inner product of two functions. So here's the notation. We use the angle brackets, then f vertical bar g. It's an integral over some interval AB. And notice here we have not f of x, but f star of x. That is a complex conjugate. Now I'm using this notation because that's what the textbook uses. But complex conjugate is also commonly denoted by with a bar on top of it. So you should be aware of that. Like this here, a bar here. And then we have this function here, w of x, which is called a weight function. It needs to be positive on the interval AB, the weight function plus it. So there are certain things that have to be defined for its inner product. Certain things that need to be specified. The interval AB needs to be made known, and also the weight function. In many cases, the weight function will just be 1. So we're just taking the integral of f conjugate of g times g. So which interval you use, your AB, that would depend on the context. So that's something that you make clear from a kind of function space you're dealing with. And if the weight function is not specified, then we would assume that it's 1. And this definition of scalar product makes sense in terms of it kind of relates to the dot product. Because what are we doing in an integral? You are multiplying corresponding function values. And if you think of this integral as a Riemann sum, you're adding them up. So this whole idea of taking corresponding components of your two vectors, multiplying them together, adding all those products, it's like you took that concept of dot product to infinity right here. So this is a natural way to extend dot product to function spaces. And you get these properties that are similar to the properties of dot product that I mentioned. You have a distributive law. You can pull apart dot products like the scalar products like this. Beware of this. It's not commutative. If you reverse the order of your operands in a scalar product, you have to take the complex conjugates. So now, if you're only working in the space of real value functions, then yes, it's commutative. But if any could be complex, then you got to remember to take that conjugate. So be careful about that. Actually, if you have a dot product for complex vector space, Cn, you have to take the complex conjugate there too. If you have a scalar on the right operand, then you can pull that out. If you have a scalar in the left operand, you can also pull it out, except you must take the conjugate. So that comes from taking properties 2 and 3 and putting them together. So again, be careful about when you must conjugate. Questions about what we define here? Now I'm about to run out of time. Yeah, I can't rush through this. All right, this is where I'll stop. So that means in my notes, I am 2 pages behind after the first day. Oh wait, check. Yes, almost 2 whole pages. I haven't decided how to deal with that yet. I don't want, that doesn't mean I want to cram in a zillion pages on Thursday. We'll see. But I'm kidding. But there'll have to be some catching up somewhere. I'll have to figure out where. Okay, but okay. Does anyone have any questions so far? Okay, I will. Yeah. All right, I'll stop recording at this point, but if anyone wants to come up with questions, I'll stick around. I'll need to be posted on Canvas on the other side.